Welcome to the first ISBA webinar. My name is Kate Calder and I will serve as the moderator for this session. I'd first of all like to thank all of you for participating and especially those who gave a voluntary contribution to the Pilar Iglesias Fund. ISBA is planning on getting into doing more webinars, and we see this as a good way to reach a large number of people as well as support some of our important funds. For the webinar today, we will have a 45-minute presentation. During this time, participants are welcome to use the chat feature on the bottom left-hand corner of your screen, but we will save all questions for the speaker until the end of his presentation, at which point there will be plenty of time to interact with him. So without further ado, I'd like to introduce our featured speaker, Mark Berliner, who is professor and chair in the Department of Statistics at The Ohio State University, and he'll be speaking on Bayesian mechanistic statistical modeling with examples in geophysical settings. Thank you, Mark.
Thank you, Kate, and thank everyone at ISBA. This is a fun opportunity. I've never done one of these, so I apologize if it doesn't go that well. If you want your money back from the Pilar thing, send me a note and I'll not answer you. I have probably more than 45 minutes of material, but that's okay. I'll just keep going and I'll pause if Kate wants me to take some questions whenever she chooses. Let's see, I can see Kate, but I can't see the rest of you, so Kate's the only person who's guaranteed not to fall asleep. So while I've been rambling here, you've seen the outline. The basic idea is to talk a bit about this notion of bringing mechanistic models into statistical models. That's hardly a new notion, but I think there's some issues and some fun stuff to talk about that's not entirely common. So I'm a Bayesian, surprise, surprise, and I'm going to be talking about the notion of incorporating my prior information in the form of the science that's available to me, or to my collaborators. I'm not a disciplinary scientist, and formally try and bring some of that material into the modeling. What you're looking at is 5 different notions of how you might do that. I don't like to overclassify or pigeonhole things, but nevertheless, here's some notions to sort of organize the thought and the presentation. The first and most obvious thing to do is to try and make explicit use of a mechanistic model. And what I mean by that is, suppose I have a differential equation that maybe is thought to be relevant to the system that I'm trying to study. I will formally try and bring that differential equation into a model. So that's what I mean by explicit. I used to call this physical statistical modeling. My common and frequent collaborator, Chris Weichel, urged me to change that to mechanistic modeling, mechanistic statistical, so it doesn't sound like just physics. This applies in lots of contexts. That number 1 there is underlined because that's the one I'll focus on in this presentation. The other ones are also relevant, however. Where did my little arrow go? Oh, there it is. Come here. Come on. So the second one is what I would describe as implicit use of mechanistic models. The idea here is that, suppose I'm doing a climate analysis. Most of you are familiar with the notion of these gigantic climate change or climate models, climate system models. Those are far too large for me to imagine bringing into a Bayesian model directly. But the challenge then would be to try and bring the information that's represented in that model, mainly through its output, into a process. And I'll talk a bit about that too, but just very briefly. Both number 1 and number 2 are an attempt to be very quantitative in the process. Of course, we've been all doing for years the use of qualitative use of theory. There's an example there that you can take a look at if you choose. But again, I mean just not explicitly quantifying things through a particular model. Depending on the complexity of the setting, there's also combinations of maybe a piece of the model is being made explicit, another piece of the model is being brought in implicitly. And then I just throw in alternate approaches so nobody got left out. When I talk about this, I try to emphasize it in two different directions, and I'll let you decide who's who. These two columns here are the notions that I try to argue about what it is that we're after when I'm talking to primarily statisticians versus what it is that we're after when we're talking primarily to disciplinary scientists. And your challenge is to figure out which column is which. So in this column, models really are important. Very seldom are models perfect. George Bach said all models are wrong, but some are more useful than others. I would argue to you that models are genuine prior information, and we need to incorporate them. Models also provide us with a nice scientific basis for prediction. So I would hardly think about predicting either weather or climate, for example, based on a purely statistical model. There might be features I might be willing to do, but not overall. Advances in both computational assets, both algorithms and hardware, as well as technology, and what I mean by that is observing systems, for example, enable richer classes of analyses than maybe we've been able to do before, and so it's a nice thing to think about looking at enriched classes, more spirited classes, maybe with space-time varying parameters and all kinds of clever things that we could not have done before computational advances. On the other column, what are the arguments? Well, the primary argument for trying to do things as a Bayesian, of course, is uncertainty management, or UQ, uncertainty quantification, as it's become rather popular to say. We all know about wonderful aspects of combining diverse information sources. I like to think of Bayes as the right basis for doing either predictive analysis or decision making. But there's even operational advantages. Things like the treatment of high dimensional parameters in a Bayesian context is very, very natural and perhaps more useful than other contexts. And I'll let you read the last one. Okay. So, Bayesian hierarchical modeling, BHM, I am not going to review much about this. I presume everybody's kind of comfortable with the basic notion of probability modeling and hierarchical modeling. What I do want to do, however, is present to you this sort of skeleton of a natural way to think about the modeling process. And it looks rather harmless, but it's actually proven to be kind of useful to organize your thoughts about the model. There's nothing very deep here. Except organization and clarification of what it is that we're talking about in a particular context. So throughout I will use as much as possible the following notation. I'll use Y's generically for physical observations. I'll use X to denote any processes or state variables that we might be interested in understanding, things like temperature, precipitation in the climate or weather's context. And theta generically denotes unknown parameters in the model. So here's the skeleton, and as I said, it looks pretty simple, but it's actually kind of useful. I will think about the data model as being the conditional distribution of the observations given both the state variables and the parameters. You might think of that as the likelihood, but I'd rather call it the data model because, well, I just prefer it, sort of. The process model then is my distribution, my prior distribution on the variables that I'm after. Again, that's conditional on theta. These thetas don't have to be the same thing, so this is a very generic use of theta. And then finally, we close the Bayesian model with a prior on the parameters. Now, of course, this specifies a joint, so I naturally have Bayes' theorem to help me do the updating and then do inference on either the state variables and or the parameters as needed. So again, there's nothing deep here, except you will see me use these three pieces of language pretty regularly as I develop some examples. And so let's take a look. In this third part of the talk, called Atmosphere Ocean Examples, I'm going to describe a kind of a little story I want to tell you. And that story is a history of the evolution of a class of models that we started studying in about 1995 when I was at the National Center for Atmospheric Research, and my collaborators there and postdocs and wonderful people all worked together, and there's been a long history of the kind of modeling that we've done. And I'll tell you that story through examples, and I'll build them up sort of in order. So this very first sort of example that we did and reached some success with is the following. We're going to try and develop a wind model, a near-surface ocean wind model for a region in the Labrador Sea. Okay. So when I say near surface, I mean what are the winds at 10 meters above the surface? That's going to be the fundamental process, and I just violated what I said. Here's W is the process. I didn't call it X. It's W for winds. And think of these as vectors with two components. Okay. Oh, yeah, I can do this. Two components. The component in the horizontal or X direction is denoted by U, and I put a little arrow here to remind us that's horizontal. The direction in the vertical or north-south direction is the component is denoted by V. These are in 2D, so there's nothing vertical here. This is a 2D surface that we're imagining. The data, there's actual physical observations that are relevant, and these are drawn from a satellite data set. There's this creature called a scatterometer, and what this thing does is it sends down, from a satellite, it sends down a beam, and that beam is scattered by the surface of the ocean. Here you go. And then scattered back toward the satellite. The satellite then absorbs that new information, and then has on board some kind of a crazy algorithm that says, well, if this is the scatter that I'm observing, this must be what the wind surface looks like. And if that's what the wind surface looks like, this must be the winds. If you believe, my famous joke is that if you believe that, you'll believe everything else I say. I say that kind of tongue-in-cheek. Over the years, that's not that funny a joke now, because I'm actually convinced that these do very well. It's remarkable, actually. Okay. Now, here comes some physics, and this is the point. I want to do something mechanistic, bring something mechanistic into a model for these winds that will help drive or steer the model toward the right sort of thing. So a first-order, large-scale approximation to the way the winds behave is something called the geostrophic approximation. And before you read that thing in quotes, just pause for a second and think about what wind is. Wind is air moving from high pressure to low pressure, basically. Okay. So that would be fine if wind would just kind of naturally go from high pressure to low pressure, except that the Earth is rotating, and so there's this Coriolis effect business that tends to bend things that try and go in straight lines. And so here's the result of some nice reasoning. The winds are linear in the gradient of the pressure field, okay? And here's the formulas that go with this. So P is a pressure field. That's a field indexed in space in 2 dimensions, x and y. The geostrophic component of the wind components, V and U, are proportional to these partial derivatives. Notice that the wind in the x direction, the horizontal direction, there we go. The wind in the horizontal direction is proportional to the derivative of the pressure field in the vertical direction, and vice versa. This constant sitting out in front is not really a constant. It depends on the latitude, but not the pressure. Okay. This thing actually kind of works pretty well at mid-latitudes, say reasonably far north, like in the Labrador Sea, but not at the surface. It tends to work at reasonably high altitudes, but certainly not at the surface. So if there's any physicists out there watching and thinking, this guy's going to talk about geostrophy at 10 meters, they would think I'm nuts, because there's friction and turbulence and it screws up this thing. Also, if the curvature of the pressure field is really sharp, then this also does not necessarily work. But we're going to proceed anyway. Here's a pictorial representation of what the problem is going to be. Here's Greenland. Oh, wait a minute. There's the boundary of Greenland. There's Labrador, and oddly enough, what's in between there is the Labrador Sea. What we're going to do is try and reconstruct winds that represent sort of average winds on a grid indicated by the locations of all of the diamonds. Okay, so there's a diamond. These arrows that you see are actually the data set. So these are these estimated scatterometer winds, okay, and you just see the vector based on the satellite, and you'll notice the way the way the locations are set up in very distinct swaths. That corresponds to the swaths that as the scatterometer, the satellite, transitioned across that section. Okay. Okay. Now, so that's going to be the winds. We have this notion of a geostrophic approximation that we don't really think is going to be very exact, but it might sort of guide the notion of how we're going to do the modeling, and that's what we're going to do next in this following order. So again, let UV be now not continuous but gridded wind vectors. These are the guys I'm after. The grid, again, is the diamonds that I showed you before. Let P also be the gridded pressure field, okay? So these, P is just a matrix sitting on top of those diamonds, and these are just vectors sitting on top of those diamonds, okay? Data model. Data, again, are the scatterometer data. Those are denoted by Y's, and I have a component of an observation in the U direction, a component in the V direction, and what I have to do is think about what's the distribution of the data, not marginally, but the data given the truth. So given the true winds at those locations, what's the distribution of the data? And what we did in this simple case is assume that the winds are essentially unbiased estimates for the data, for the truth, sorry. The data are unbiased estimates for the truth, and they all have independent measurement errors. This K thing, we call it a mapping matrix, and that's necessitated because of the mismatch in the gridding here. We did a very simple thing here. We sort of just moved these things over to the grid boxes that are close to them, okay? And that's the function of K. Now notice something. I mean, please notice that I'm saying that the winds are conditionally independent. I am never going to tell you that the winds are independent in space. Again, take a look at this. Obviously, there's a great deal of structure. We see a lot of high winds where that little arrow is, and there's a lot of high winds near that. Same thing over on this guy over here. You can see a lot of structure. So certainly the winds are not independent. We're saying that they're conditionally independent, and it's a very different statement. Oop, wrong way. Okay. Now here comes the fun. The process model is again going to be based sort of on geostrophy, and I just in parentheses reproduced the geostrophy relationship for you. But we're going to discretize that thing. We're going to approximate partial derivatives, those partial derivatives by discrete derivatives, okay? Just local changes in the value across grid points. And then we're also going to do something else. We're not going to use the C that's dictated by the theory of geostrophy. What we're going to do is put some parameters out in front and let the data sort of inform about what those coefficients should be. So again, what I see here is something like, when I'm looking at the geostrophy thing, I see something like the UV winds being proportional to derivatives of the pressure. Discretized, I now see the winds as being sort of related to, again, don't forget this is not the pressure, but the differences of the pressure, okay? And that's our representation, or we call it stochastic geostrophy. We are, this is kind of funny notation here, What this says is that at a point, the U wind, V wind at a point are dependent, but conditionally from point to point they're independent. Okay. Okay. Well, this sounds fine, but all I had was wind data, so I better do something about the pressure field. I've introduced this field that I have absolutely no information about in principle, and so I have to endow it with some kind of a distribution. And in this example, we found a nice spatial model in some work by Jean Tiebo, and we incorporated that into and built a prior for P. Okay. And then, of course, we got to put a prior on all the parameters, the variances, the coefficients in this part of the model, etc. Okay. Well, here's some results. This is our Bayes reconstruction, and this is just the posterior mean. What you see now are the diamonds are gone, but the diamonds have been replaced by the locations of these wind arrows. These are our posterior expectations of the winds. The contours are actually our posterior expectation of the pressure field. Okay, wait, pressure field, there's no pressure data. Well, I don't need pressure data, I'm a Bayesian. I have wind data and I have a relationship between winds and pressure. So not only can I use that relationship to tell me something about winds off-site, but I can actually reconstruct something about the pressure field. Okay, and let's see, take a look at this region, and you can see a storm. You can notice that the winds are revolving around here, right? Are revolving counterclockwise, and so that's a low pressure system in the northern hemisphere. And it was actually in the data originally as well. There it is, still in the arrow. Okay. So that's a quick start on this notion of bringing in some kind of physics. Please note we're not using the physical model exactly, but it's motivating something. The next piece of the story then is this creature, a near surface wind model again, but this time in the tropical Pacific. Before I go any further, it's in the tropical Pacific, so geostrophy is not going to work. Also, we're going to try and do this in space-time. The geostrophy was a frozen in spatial model. Now we want to do space-time prediction. This paper has actually been around a long time. It's in JASA, and statisticians can look it up really easily. Okay. This time we're going to do two classes of observations. Again, we're going to have those scatterometer pieces of data. Those are sort of high resolution in terms of their spatial distribution. We're also going to use a collection of data that's not very commonly thought of as data by statisticians. There's major weather centers throughout the planet. The European Center for Medium Range Forecasting and the National Centers for Environmental Prediction in the US, for example, that produce assimilated output. And what this assimilated output is are essentially guesses based on a very, very complicated model and data of the values of various physical variables on a very global scale, but at low resolution in terms of space. And let me show you what I mean. Here's what I mean. Sorry. So the left-hand column are representations color-coded by magnitude of U wind data. Okay, remember U winds are horizontal in the X direction. U wind data on these analyzed fields. So you can think of them as sort of a process. They're statistics. They're definitely a function of observations, but they're very complicated functions of observations. And I hope you can see the structure of the gridding there. It's very coarse. Oh, in case you're not locating things, that's Australia, of course, New Guinea, and Asia. So what you see here are 6-hour time shots of what the National Center for Environmental Prediction would have guessed winds to be on that grid. In this column, you see, it might even almost look like it's kind of almost continuously filled in. You see swaths of scatterometer data. This is from the satellites. And notice that they're much finer in spatial scale, but they're very intermittent temporally. Okay? So I have very fine scale information over here, almost no information in this particular spot. There's one little swath right there, and then several swaths in the other direction, ascending and descending as the satellite moves along. Horizontally, these match in time, and I just pointed to the screen, and I guess you probably can't see that, but I'll keep doing it probably. Oop. Okay. So this one gets a little sophisticated. Again, data model, process model. The data model is going to be fairly simplistic as it was in the previous example. Gaussian measurement error. That is, the data is assumed to be equal to its mean, and the mean is the wind process, and then some Gaussian measurement error noise. That's actually been suggested in the literature, and so we're not very worried about that particular data model. The process model. Again, we're after, first of all, we're in the tropics, and second of all, we want space-time, so we have to be a little bit more sophisticated in the kind of modeling that we're going to do. The experts in this stuff, Chris Weichel and Ralph Milloff, suggested that we look at something called shallow fluid equations. Remember that we're after winds at 10 meters, and so you can think of the atmosphere very close to the ocean as a narrow band. The atmosphere is a fluid. It's just not a very dense one. But the atmosphere is a fluid, okay? And it's very shallow in the sense that we're interested in that portion of it that's near the surface of the ocean. Turns out that there's a set of equations, and I didn't even reproduce them here. But what we did with those equations is linearize them, okay? Linearize shallow water equations, and those linearized equations you can actually get the solutions out. And those solutions actually line up on something called modes. This takes a little bit of practice if you're thinking about things. The parallel I like to make is think of these things almost like if this was one dimension, think of a process running around that's sort of like a bunch of sines and cosines. That's hardly the right thing to do here. But we do get modes out of this thing, and think of those modes as vectors distributed in space that capture large-scale space-time variation of whatever shallow fluid you're modeling. Again, large scale. There's also a lot of small-scale stuff, and again, you can keep going back to this in your mind. There's a lot of small-scale stuff, and what we did for the small-scale stuff is just use a wavelet model. Okay? So that combines to the following notion. We think of the winds, and here I just wrote down the V winds at a particular time point, okay, as being equal to this large-scale approximation plus something at the small scales, the wavelets. Whoa, let me pause for a second and let you ponder that. So there's a large-scale component into the winds based on the solution to this physical model, and then there's some other stuff at small scales that we're not going to put a physical model on directly, but rather use multi-resolution wavelets as a flexible class of statistical models. The one thing that you really need to take, I know there's not even looking at the differential equation, this might be kind of quick, but the one thing I'd like you to take away from this, and I'll mention it again later, is the coefficients. This cap phi is a matrix whose columns are these modes. Actually, if you like, think of them almost like principal components. Okay, that's a very nice kind of statistical notion. They're not. They're something a little bit different. But think of them in that way. So I have a collection of vectors that represent the large-scale behavior, and then a column of coefficients on them. Same thing here. These are the multi-resolution wavelet function bases, and then another collection of coefficients. Here's the key. Phi and psi do not vary in time, but we do make the coefficients vary in time. Okay? So in fact, the A coefficients, the coefficients in the large scale, are going to be modeled as an autoregressive process for the A's and another autoregressive process for the B's. So here's the space stuff, those two guys, and the temporal part of the model is this. Please note that we're not separating space-time. This is not a space-time separable thing. It's a different kind of view of how we treat the space and the time. And then we do something similar for the U-winds. Again, we have these large-scale bases and then wavelets. There's a great deal in the paper, and needless to say, I'm dispatching that discussion by just telling you that there's a lot of theoretical and empirical science that goes into the discussion about the parameters on the priors, the priors and the parameters. Parameters and the priors, that what you guys do. And I'm just going to skip that. My emphasis is this equation, okay? This comes from physics, but it's not exactly what the physics says. The physical model would actually dictate what the A's should be, okay? We're not going to use what the physics dictates the values of the coefficients. We're going to do something else. We're going to let the data train the coefficients. Oop. So here's some results. This is a particular snapshot in time. It would be nice to watch a movie of this, but I don't have one. But here's a particular snapshot in time. This is an instant. This first graphic is the so-called NCEP data, right? Those are those analyzed fields that we get from this large weather center. And you can see with the wind arrows, okay? That's their estimates. Please note again, that's a very coarse grid compared to the grid that we're after, or compared to the grid that you would see from the scatterometer. That's much finer scale, okay? Our gridding, the grid on which we do the analysis, is this one. And you can see there's a lot more arrows. You can't probably even tell which direction they're going, but there's a lot more arrows. That scale is in between the scatterometer scale and the NCEP scale, okay? It's in between those two. And here's our reconstruction of the winds. Much finer. This is a posterior mean, okay? Here's a couple of ensemble members from our MC for that same instant. And here's the posterior variance point by point, posterior standard deviation point-wise. Okay, let's take a look at this. So the first thing to see is notice this very dark area, this structure, okay, that we see in curvature of what looks like a very interesting weather event. In fact, there is a very interesting weather event, and this picture is an indicator of this. This is cloud top temperatures taken at the same time, and so think of that as the kind of thing that you see on the Weather Channel all the time, just a remotely sensed picture of clouds, and you can see, if I had it right, the drama would be to slide this picture down on here and you would see them almost coincide, okay? Notice that you can't see that structure in the NCEP data. It's simply too coarse. You might say there's a little bit of something there, but it certainly isn't nearly as refined as this or this. The other thing, these realizations suggest to you sort of that the structure that we found here is actually really there, okay? That's not an accident of averaging. Essentially all of the ensemble members really do, well, not all, most of the ensemble members of the MC samples really do find that structure, okay? It's there. How about the standard deviations? So notice that there's color schemes here. This area, it might look a little green to you as opposed to this yellow area. What's going on there? That's a quick question. The green area corresponds to smaller standard deviations than that. And what that corresponds to is regions where we had scatterometer data roughly corresponding to that period. So when we had scatterometer data that was relevant to that spot, okay, not surprisingly, we get a better posterior standard deviation. Okay, so let's recap. Simple model, geostrophy, purely spatial. Now we advance that and use a lot more physics, and we're pretty proud of these results. You can look in the paper and see that there's even more interest. We think very, very nice results, but more sophisticated physics. Okay, so we were so enthused we decided to just keep going and started to think about an even more challenging problem. And that challenging problem is to try and model both the atmosphere and the ocean. So just intuitively, just think about this. Near surface winds blow across the ocean and of course drive the top and maybe generate wind blowing currents, okay? And so I might be able to say something about the behavior of the ocean, the behavior of the ocean given near surface winds. The ocean also impacts the atmosphere. We all know about heating from the ocean, creating, eventually generating all kinds of interesting storms, sometimes not so pleasant storms. But we might be able to say something about the winds given the ocean, okay? And so we would like to do some modeling here and do some statistics, Bayesian statistical modeling, to try and link these two processes. It's not very easy because the physics now is going to get much more complicated, and also things happen at multi-scale, both in space and time. For example, the ocean operates at a much slower clock than the atmosphere. So there's often a mismatch in important features, but that's maybe another story. You'd think I'd get used to this by now. So I'm not going to talk about this. I put it up just to beat my chest and the chest of my collaborators. We developed a testbed model. This is not very realistic in terms of full data, but a testbed model that links ocean and near-surface winds in a process not called geostrophy, but something called quasi-geostrophy. And this is complicated enough for me to just say, I'm not going to review it for you. But you can stare at this partial differential equation and hopefully recognize that this is not so easy. This psi parameter, or psi process, is some feature of the ocean. Notice that the model for the evolution of that feature of the ocean depends on winds through this curl, okay? So here's where the winds enter this process. What we do, and this took a long time, is generate a model for the ocean given the winds, and that's based on discretizing, again, in space and time, this equation, okay? And to that, we then need to couple a model for the winds by themselves. But we've had a lot of experience in modeling the winds. That's part of the story. So for example, that wind model that I showed you in the first example, the so-called Royal model, that, as I'll talk about it, in the Labrador Sea model, if I just want static winds for a second, I might use something like that in the Labrador Sea to generate winds, and then use those to move into the ocean problem. If I was in the tropics, it's not clear I would use this particular quasi-geostrophy model, but if I was in the tropics, instead of using something like the Royal model, maybe I'd use something like the Weichel model, the one I just reviewed for you. Okay, so now let's see if we can even do this, take this further. Here's perhaps the most aggressive and large-scale project that we've entertained in this physical modeling stuff. We're going to try and do some Mediterranean ocean forecasting system, Mediterranean ocean forecasting. Here the idea is as follows. As I said before, winds, which we know a lot about, serve as a boundary condition for the way the ocean surface works. If I have an ocean model, okay, the ocean model that we're going to look at is a gigantic, it's one of these supercomputer models. It's a gigantic supercomputer model. It's large scale, it's deterministic, and it models the Mediterranean Ocean in 3 dimensions, horizontal, vertical, and down in depth, and in time. So it's a huge creature. However, maybe we can do hierarchical Bayesian modeling in support of the use of this gigantic deterministic model. And the way we can do that is to construct winds, okay? Get an ensemble of winds, use a Bayesian model to get those winds, then insert those winds into this gigantic model, and what do we get out? We get Bayesian hierarchical modeled oceans, okay? Then we have another problem about combining those results, and this is the topic for another talk. But the arrow is as much as I want to show you today, okay? So I hope the structure is clear. Let me show you a little bit more about this. This is a very large collaborative project with Nadia Pindardi in Italy, and her group, and then our group here in the States. And here's a picture that you probably can't see, so I won't ponder for long. What we're going to do is something very similar that we did in the Weichel model. We're going to have scatterometer-based information about winds over the Mediterranean. That's actually a representation of the Mediterranean. Here's that's the Mediterranean. That's actually the Pacific. Yeah, good geography, Mark. That's the Atlantic, and there's the Straits of Magellan. Strait of Gibraltar. I have the Pacific in mind here in a second. Okay. So these are those fine-scale scatterometer data, and then we have, instead of NCEP in this analysis, there's a European model that produces winds, but at a coarser resolution. Before we came along, they would use these winds to drive the ocean model. Physics. Okay, so how many wind models have you seen? And this is part of the point. There's no such thing as the model. Okay? The model that you're going to use for a given process depends on the purpose, the location, the physics, and the data that you're going to have in mind. So in the Labrador Sea, you saw geostrophy. In the tropics, you saw a completely different model. In this Mediterranean region, we use even another model. This is a bit more enhanced. It's a more a bit more to it than the geostrophy model, but it's not quite the quasi-geostrophy model. Okay, it's called a Rayleigh friction model, and we found that we needed this to get some decent winds in the Labrador Sea, in the Mediterranean. I'm really confused in my geometry this morning. Where's my coffee? Okay, so let's, again, this is way too much mathematics and notation to follow through, but there's some theory. You recognize some U's and some V's. Those are the winds. Do some approximations, discretize things. That's this line, these lines, and then use this to motivate a statistical model. So we have an autoregressive model. V depends on the previous V, depends on some pressures, previous pressures, and some noise. Okay, so it's a stochastic model. This is not a stochastic model, but we made this into a stochastic model. Okay, everybody's clear in that physics, so I can go on. So here's 10 members from our posterior distribution for a particular region, for a particular time point, and you can't see any of this, I'm sure, but here's a portion of the Mediterranean, and what's actually sitting here are 10 ensemble members at each of those locations, and I can barely see what that is, so I won't I won't stay there for long. I'm going to show this slide because Nadia and Ralph and Chris would be better at explaining this to you, but they like these pictures, and what you want to take away from these pictures is that by using these Bayesian winds that we produced as initial conditions and then bringing it forward through the model, we're getting more realistic behavior in the resulting oceans. We're getting that we can represent some extra uncertainty and variability at the right sort of scales and locations in the model. If you just use the European center winds, you don't get this, at least not as good. Same basic idea, and I won't repeat it because I don't know what the hell I'm talking about. This is just kind of an interesting picture. Again, we're just doing the winds over the Mediterranean at the surface, but you can take a vertical line on the surface and then take it down in depth. This is going down to 500 meters. And so you can think about this as the propagation of our Bayesian winds through the model down into the ocean. And we can even get an uncertainty about that. So we like that. I'll skip that. That's a little complicated. So here's some discussion about what's the good stuff and a couple of references if this attracts your attention. There's a couple of papers in the Journal of the Royal Meteorological Society that describe much more detail about this modeling and its impacts. Okay. I got more than 5 minutes. Who's going to stop me? They could always turn off my computer. A little change of pace. So that was the story. Very humble beginnings in the Labrador Sea all the way to this gigantic Mediterranean Ocean forecasting system. I wanted to show you a very different sort of an example, just to show you, again, the sort of thing that's possible and the directions that you can take some of these things based on simplistic modeling. So the last example I wanted to show you today was this glacial dynamics example. And the idea is this. We're going to try and use simple models to try and understand how glaciers on a very broad scale flow toward the ocean. Okay? Well, what controls that flow? You can think of glaciers. Actually, let me just show you the picture. This is where our data is going to be. This is a region called the Northeast Ice Stream. It's in Greenland. What you want to look at on the top here is data-based estimates of the surface of the glacier as it's moving in the horizontal direction. So this spot is the top of the glacier. Here is almost the bottom as it's moving toward the ocean. And we're sort of running this down a center line of this ice stream. Okay? So here's what the surface looks like. And what we want to do is understand how that whole thing is sliding from its beginning down as it goes toward the ocean. Long-term goals are to, if we can understand the parameters that control that rate of sliding, then we can maybe understand what's going to happen under climate change issues. Okay. Okay. So what we're going to do is make a very simple model. Again, we just have this slice going down the center of the glacier toward the ocean on its main direction. And why is it flowing? Well, it's flowing because it's being pulled down by gravity. The glacier starts higher and is heading toward the ocean. And so it's being pulled down by gravity, but it's also being held back by drag or even friction, if you like. So it's being held back at the base, the bottom of the glacier, or the ice stream, and also on the sides. So the flow to a first order is gravity moderated by drag, but there's and then a bunch of other stuff. Okay, it's almost solid, but it also behaves much more like a very viscous liquid. So there's a bunch of other stuff. This is not the complete model. But it does suggest that we can get approximations to the flow from very simple models that are just based on geometry. What is the shape of the base? What is the shape of the slides? And the region that it's flowing across. So what we have is a collection of data. We have some observations of surface topography. That's the first picture I showed you, actually, the top of the glacier, or the ice stream. We have some data about the base. And then we have some data about the velocity at which this thing is moving toward the ocean locally. Okay? Remember, it's not exactly solid. So at the surface, it has different velocities as it moves toward the ocean. Okay? And those are based on interferometry. Okay. I'm getting tired. So here's again the surface data. Here's the base, and if you can't see this, please note that the vertical coordinates here are in meters. Okay, the horizontal is in kilometers. So this is 400 kilometers horizontally. Okay, So over this 400, so this looks very mountainous, but it's not, right? Over a 400-kilometer run, the base is varying on the order of a kilometer. Also notice that the glacier, or the ice stream itself, is on the order of a kilometer in thick. Okay? Okay. I'll show you the velocity data later when I reconstruct it. So again, try and find some physics that will help us understand what's going on. And your glaciologists give you some books, and then they also give you lots of talks, and hopefully you catch on, and you begin to realize that there's some basic modeling to do. And that basic modeling does the following. You can think of the surface velocity, okay, the surface velocity of the glacier as being composed of the sliding velocity at the bottom, that's u sub b, plus some stuff. And this stuff is all not all of them, because there's going to be some error. This stuff is based on some approximation of physics. It's based on some somewhat like solid mechanics, stress tensors, all that good stuff. We don't need to worry about it. I think of this as the height of the glacier times something that's pulling the glacier back, okay? So this is almost sort of like weight, but don't worry about it. Anyway, what you want to take away from this is a simple model that looks at the thickness of the glacier and then some stuff that's a function of thickness and, interestingly enough, the derivative of the surface. Go back. Whoop, wrong direction. So the derivative of the surface and then something about the thickness are extremely relevant in this simple model. And it's based on a bunch of stuff that I'm not going to talk about. Okay, our model. Well, this is a deterministic model, right? This one. Our model is not going to be deterministic. We're going to make a model for this so-called stress, or it's not really a force, but a stress on the glacier that's going to follow very much what they did, okay? But we're going to add some error, eta. We're going to add an error process. We call it a corrector process. That's going to cover us a little bit for model error. Also, the thickness is not going to be known to us. It's going to be a random variable. So here's what a trick I've learned. Whenever you write down a physics model like this one, think of this as the conditional distribution of this quantity, this stress, conditional on the thickness and the surface. Okay? And if you do that, then you can begin the transition from these physical models to nice probabilistic models. We're going to make a random thickness, and we're going to use a wavelet model for that. We need a surface and a derivative of the surface, and we got a parameterized model from the literature that works pretty well. And then we put all this together into a nice random velocities model. So please note all the sources of randomness here. This thing called tau is going to be modeled as the physical thing plus a correction. That's going to be stuck in here, but then we're also going to put some error into the velocity model. When you do this thing, it's also a really good idea, at least in my opinion, to go and make sure, because you write down these formulas, make sure you actually have a model. So what the model here is the hierarchy is that we're constructing a distribution for velocities given surface and thickness and the corrector, and then separate models for the corrector and... Kate, did you just come in? You want to do something? What? Oh, pish posh. Okay. All right, I'm going really fast now. So here's a smooth base. If you don't smooth the base, all this physics fails. If you leave all that data really, really jagged, okay, it'll fail. So you have to smooth a little bit. So we made a Bayesian wavelet smoother. The very sharp things are the original observations. The red line is a smooth version of that, and that's what goes into the velocity model. When I give this talk to physics communities, it's this picture that I really am the most intrigued by, and they're the most interested in. This is that thing I call the corrector process. It's the correction to the physical model, and it gets a posterior. And so what I really like about this is this thing, I should have put a horizontal line here at 0. This thing kind of indicates to you regions where that simple model is tending to fail, at least as far as the data is concerned. Okay? This part, ignore. That's all of this physics fails when it's too close to the beginning of the glacier, so I'm not worried about that. But you'll notice this region where I need to make the stress tensor a little bit bigger here, then a little bit smaller, then a little bit bigger, a little bit smaller, etc. And what we think is going on is that this might actually be finding places where the glacier is either sliding or slowing down due to lubrication at the base, at the bottom. So if there's a puddle of water at the bottom, this glacier is going to move a lot faster in that region. And we're hoping that this corrector process is actually indicating that. And that's pretty cool because don't forget this thing is about 1 kilometer thick. So we might actually be finding lubrication at the base. That's really important in climate change because as the planet warms, we see more and more lubrication, and we see these things zipping much quicker toward the ocean, and that's actually correct. There, somewhere in here, there's a blue line. That's the velocity data and our reconstruction for it. And I'm out of time, so I'll just tell you that that's a great result. It's actually not bad. It did pretty well. I guess I should stop. So somebody please ask me about the things that I was going to do here afterwards. And that'll give me time to explain these little discussion points. Thank you. Now what do I do, Kate?
Okay, so now we have some time for questions. Questions can either be asked by raising your hand or by clicking on the little person icon at the top, and I can transfer microphone access over to you, or they can be asked by typing into the chat window. So are there any questions?
Put my slide back up. Unless you're not getting any questions, let me just... This page is almost the most important. Am I still on? Can you still hear me?
Yes.
Let me just say a couple of things while you're pondering your questions. I hope I didn't do this too quickly and not let you take something away. So here's at least a few things to take away. Number one, if Bayesians can bring something to this modeling strategy that is richer than either the physics that underlies the process or the statistical modeling. I know that's a pretty pompous thing to claim, but I actually believe it. So again, think about the Weichel tropical winds model. If you just stay with the physics, you get those nice large-scale modes from theory, and you get coefficients in front of them from theory, but then you're done with it. By taking that out, but then leaving a statistical model that can train the coefficients, then you're getting something from the data, and the data can respond to whatever's locally going on in space and time that the original modes maybe don't respond to. Another version of that is in this paper. I didn't talk about it, but another thing that we can bring to the table that you can't really do very easily without these mechanisms is to put spatial temporal models on parameters. Not just spatial temporal models on the processes, but on the parameters. One thing, if you get into this business, that you need to be careful about is the difference between, if you're incorporating a PDE, you need to be careful about the difference between trying to solve a PDE versus using the PDE to guide the process model. In the examples that we showed you, we do not use a finite enough space-time grid to claim to be solving the partial differential equation. Okay? So from an applied math point of view, We're not solving the differential equation. We're using it to guide a stochastic process model for the process that we're after, but not solving the differential equation. I didn't talk about it at all, but needless to say, the more complicated these get, the more challenges we get to approximate Bayesian computation, and that's just a delightful area to think about in this context. You have to do all the usual stuff that you do in statistics. Just because the model's coming from some physical principle doesn't mean it's a good model. As you can tell, I think I'm talking to statisticians. So all the issues that we do about model assessment, model selection, are still relevant. You have to be good statistical practice, and not forget about that. Okay, did any questions come in while I did that? Kate?
Yes, there is one question from Renata Rotondi. She asked, do you have any experience on applications in seismological fields?
No, but I just got a request to look at some. I don't. Sorry. I know there's a couple of things that would be really interesting to do, but I have not looked at it at all. Send me something and I'd love to read about it. But no, I don't have any such experience.
Other questions? Renata is responding. And Marlise Clyde is typing.
Hi, Marlise.
So Renata asked, the problem is that we do not know a physical model in seismology.
But there's a great deal of qualitative understanding. I know. I understand what you're saying. I mean, there's nothing nearly as sophisticated as some obvious partial differential equation, the kind of thing that we can get from continuous space-time for temperature and pressure fields and all that good stuff. But surely there's something about the model, about modeling that is accessible. I saw people actually trying to understand, as people learn much more about the geometry along fault lines in very high spatial resolution, it may be actually possible to begin to think about models for slippage if you can really understand the structure in a very expansive yet fine scale behavior along a fault.
Renata says thank you.
Okay. Well, you're welcome. I wish I could tell you more. Keep me posted. If you get something, I'd love to see it.
And Marlise, do you have a question? Marlise asks, what advice do you have for graduate students who are interested in research in this area? What background is valuable and how much can they pick up along the way?
Certainly, if it would be really nice. I don't think you have to do applied mathematics I like it. I certainly have done applied mathematics and would encourage people, if they have the time, to try and do something about numerical solution of partial differential equations. But honestly, I don't think you need to. At least to the experience that I've had, a lot of my statistically trained collaborators had no prior experience really. It may take a little bit more time and a little bit more patience, but I don't think you need to be a physicist or an applied mathematician to do this. I would focus on richness of stochastic modeling and also computation. The challenges of developing the appropriate ABCs or MCMCs for these things is critical. If you really know that you want to go into climate or weather applications, and those are huge areas, then at most universities I think you can find a really nice introduction, say, to climate science. And I think that would be an excellent use of your time. The reason I would suggest that, if you had to make a choice between that or a differential equations course, I would pick a climate course, because you'll see much more of the specifics of the modeling, but you'll also get into the language that would help you understand and communicate with climate scientists. And also find somebody to mentor you. That helps a lot.
Are there any other
Are there
questions?
any other questions?
Okay, if not, I'd like to thank our speaker,
Thank our speaker.
Mark Berliner.
Mark
We
Berliner.
greatly
We
appreciate
greatly
his time,
appreciate his time.
and
And,
we hope you'll join us
we hope
for
you'll
a
join us
future
for a future
webinar.
webinar.
Thank you.
Thank you.
Thanks, everybody.